Okay, let's first recall what we had last time. Last time we introduced the eigenvalues and eigenvectors of a matrix. Okay, the idea is we want to find invariant of certain operations. Okay, if we view a matrix A in by N matrix as a rule such that you input a vector, then output the A times this vector. Now we want to find a special kind of vector such that the direction of this vector is invariant under this operation. Okay, so the output is scale. Okay, a multiple of this vector by a scalar. So the direction is the same. Okay, so this is definition of vectors, eigenvectors, and eigenfunctions, eigenvectors and eigenvalues. And then we give several examples of eigenvalue and eigenvectors. Okay, for instance, we have the magic square. Okay, the magic square. Okay, this is really old. The magic square is really old. So some story about this magic square. It was believed that this thing was something that people see on the turtle, on the back of a turtle. Okay, and in ancient time, mathematicians, they are related with fortune telling actually. And this thing, this object, this magic square is somehow is related with that thing. Okay, so if we have this magic square, then it has the sum of the diagonal with the sum of the column vector, they are the same. We get a 15. So if we have vector 1, 1, 1, okay, so you see A times V. This is we get a vector which is the sum of the column vectors, okay? Because now each component will be the sum of the rule, okay? Sum of the rule, because every rule is the same sum, 15, okay? So we get it. This is the 15 multiple of 1, 1, 1. So we have, an eigenvalue 15 and an eigenvector 1, 1, 1, okay? Now this one, Sudoku matrix. Now, every column and every row is a permutation of 1, 2, 3 of all the way to 9. Okay, the sum of every row is sum 1, 2, 3 all the way to 9. So if you have this vector V, which is a 9 component, okay, all the ones 9 component is 1. Okay, then if you multiply A by V, okay, A times V, now this you get actually the vector. Now each component is the sum of 1, 2, 3 all the way to 9, which is 45. So you get a 45, 45, 9 45. So this is actually, if you factor out 45, so you get a 45 times V. So this you get a eigenvector V and an eigenvalue 45. Now this is some special example, and we can obtain this special eigenvalue or eigenvector by observing the symmetry. Okay, observing the symmetry. Now the matrix A, a Sudoku matrix, looks like a random. However, it does have some symmetry. Okay, if we rearrange the thing, so we get some symmetry. So matrix, for a matrix, the eigenvalue, the eigenvector actually tells us some global structure related with this matrix. Okay. Okay. Now if we have a general matrix, how do we actually find its eigenvalues and eigenvectors? So the following algorithm, we use the following thing. So we use this. Remember, eigenvector is by definition is non-zero vector. Okay, we don't want 0 because 0 is trivial. So in the definition we assume eigenvector is non-zero. So if AV is lambda V, then V is an non-zero vector V. V is an eigenvector with eigenvalue V, with eigenvalue lambda. So if you write it as A minus lambda I is identity matrix, okay, times V is 0. So we get actually the matrix A minus lambda I has non-empty null space, okay, because V is non-zero vector lies in the null space. So we know the matrix A minus lambda I cannot be full rank, okay, it is, the null space is non-empty, so the matrix is singular. So this tells us that the determinant of this matrix A minus lambda I vanishes, okay, 0. Now this is, you can go backwards. So the determinant is 0 means the null space is non-empty, okay, that means the null space is non-trivial, okay. So there are non-zero vectors lies in null space. And then we have an eigenvector. So to find eigenvector and eigenvalue, it suffices to solve this determinant, this equation, determinant A minus lambda I be 0. Okay. Last time we give one example. Okay. Today we will continue with this eigenvalue and eigenvectors. Now we will do examples of eigenvalue and eigenvectors. So let's see this example. Let's see this example. Let's assume this matrix A, for instance, this matrix A, a 2 by 2 matrix. Okay, so it's a 3, 3, -1, -1. So we find its eigenvalues and eigenvectors. Okay, find eigenvalues and eigenvectors. Vectors of A. Okay, now to find eigenvalue and eigenvectors, the first step we find the determinant. Okay, A minus lambda. So A minus lambda I, this will be the matrix. This matrix A. Okay, minus lambda I. So it's lambda here, 0, 0. Okay, diagonal matrix with diagonals lambda. Okay, so this will be 3 minus lambda, 3 minus lambda, -1, -1. Okay. Now the next step, we find the determinant of this matrix. We assume the determinant should be 1 is. This is the determinant if you use 3 minus lambda, 3 minus lambda. So here -1, -1. So this 2 by 2 determinant. So we get 3 minus lambda minus 3 minus lambda minus -1 times -1. Because 2 by 2 we have definition, okay, determinant. So this we get if we rearrange this. So this you get 3 minus lambda squared minus 1. So expand this, or you factor this, use difference of two perfect squares. So you get this is 3 minus lambda minus 1, 3 minus lambda plus 1. Okay, so this will be 2 minus lambda, 4 minus lambda. Okay, so to find the eigenvalue, okay, so we let the, so we assume this determinant should be 0. Okay, let the thing to be 0. Let me find two eigenvalues. Okay, so we let determinant the thing to be 0. Determinant of A minus lambda I to be 0. Then we get this equation. Okay, this equation. Then we solve this quadratic equation. Then we get two solutions. Lambda 1 is 2. Lambda 2 is 4. Okay, two eigenvalues. Okay, and then if see what happens if we get lambda 1 to be 2. Okay, then A minus lambda 1I. So this will be A minus 2I. Okay, A minus 2I. So A is, remember A is, remember once again, so it's 3, 3, -1, -1. So A minus 2i, so this will be minus 2 in the diagonal. It's 1, 1. The off-diagonal terms are keep fixed, okay? So you can easily see the eigenvalue, and so you can easily see the eigenvectors, okay? Easily see the eigenvectors. So if A minus lambda I1 V to be 0, let's V to be 0. So here V is xy, V is xy. So you got a x, so this matrix y negative 1, negative 1, 1 minus times xy is 0, 0, okay? Now what you solve is you get the equation 1 is you get x minus y is 0. Equation 2 you get a negative x plus y is 0. So they are not linearly independent, of course, because it's singular. So actually we only solve equation 1. So we get y equal to x. So this the value, the vector will be xy will be xx. So it's x multiple of 1, 1. Okay. So the eigenvector we can choose. So we can choose eigenvalue. So the eigenvalue is 2 here. Eigenvalue, in this case, one eigenvalue is 2. Eigenvector. Now remember, eigenvector is non-zero. Okay. So if you have an eigenvector, you multiply it by any non-zero scalar, then you get also an eigenvector. So eigenvector only we can only define its direction. Okay. So you can multiply it by any scalar, x multiple of 1, 1. So here x is in R, x is non-zero. Okay, x is non-zero. So it's in the direction 1, 1. Okay, another eigenvector. Okay, so eigenvalue, if eigenvalue is 4, then remember A is 3, 3, 1, 1, negative 1, negative 1. So A minus 4i will be minus 4 in the main diagonal. So 3 minus 4, we get negative 1, negative 1. Now all the diagonal terms are fixed, okay? So you see this is, we can also easily find its eigenvector. That's very easy. So negative 1, negative 1, negative 1, negative 1 times xy equal to 0, 0. So we get solve this equation. Then we get a negative x minus y is 0. The second equation is just identical. Okay. So we get actually y equal to negative x. So the vector xy will be x negative x. Okay. If you factor out x, so this will be x y negative 1. So the eigenvector will be so eigenvector in this case. So eigenvalue in this case, eigenvalue equal, we take it to be 4, and eigenvectors will be corresponding eigenvector will be x multiple of 1, negative 1. Okay, here x is in R, real number, any real number, non-zero. Okay, non-zero real number. Okay, then we are done for this example. Okay, now the key thing is try to find the root. Try to find the root to this thing. Okay, if we have a matrix A, this thing is called characteristic polynomial. Characteristic polynomial. Find root. Characteristic polynomial of the matrix A. Matrix A. So we find roots. All roots of the characteristic polynomial of this matrix A. Okay. The characteristic polynomial is a polynomial in lambda, in variable lambda. Okay. So let's see this example. Okay, example. Let's take a 3 by 3 matrix. Okay, a to be 2. Now for 2 by 2, the characteristic polynomial, you get a degree 2 polynomial. Okay, if you get a 3 by 3 matrix, then you get a degree 3 polynomial. Okay, n by n matrix, its characteristic polynomial is in degree n. Okay, degree n. Now in general, to solve, find the roots of degree n can be hard in general. Okay, especially for high degree greater than 5. In that case, there's no general solution by solving by radicals. Okay, so degree 2, we have a quadratic formula. Degree 3 and degree 4, we also have a formula. Okay, determined by the coefficients, solving it by radicals. It's complicated. Degree 3 is reasonable. Degree 4, actually you can use the trick to transform to degree 3 and then solve degree 3. Degree 4 is complicated if you write it down explicitly. I think once people, this is really old, okay, several hundred years. Okay, then when people finished degree 3 and degree 4, when people trying to solve degree 5, try to find a formula using radicals. Then people finally, two mathematicians, Abel and Galois, okay, they both proved that degree 5 in general, we cannot solve it by radicals. Okay, the solution, the roots are there. There are roots, but we cannot solve it by radicals. Okay, it's a number that you cannot write it in terms of radicals of coefficients. So in general, find roots of polynomials can be hard if the degree is higher. Okay, here degree 3 is reasonable for this example. Okay, then we find the determinant of the characteristic polynomial, determinant of a minus lambda I. So lambda I is the diagonal terms are lambdas. Okay, so a subtract the diagonal terms lambdas. So a will be the thing. So we subtract the diagonal terms of a by lambda. 2 subtract lambda and -1 subtract lambda. Then all diagonal terms we just keep it as fixed. Okay, keep it as fixed. 1, this is 3. Okay, now we can compute this determinant, use Cramer's rule. Okay, use Cramer's rule. Using the definition of a determinant. Okay, now here we can explain. That's easy because here it is an upper triangular. The upper triangular matrix, its determinant will be the product of the main diagonal terms. Okay, because it's upper triangular. So here we have 2 subtract lambda, 2 subtract lambda, the product of the main diagonal terms. Okay. Okay, so we let the characteristic polynomial will be what we just write. Okay, 2 minus lambda times 2 minus lambda times -1 times -1 minus lambda. So this is the characteristic polynomial of the matrix A. And then we find the roots of this characteristic polynomial. So if we let this polynomial to be 0, okay, minus 1 plus lambda to be 0. So let this thing to be 0. Let me find lambda 1 equal to lambda 2 equal to 2. Okay, so here we have multiplicity for certain eigenvalue. So lambda 1, lambda 2, they are the same. Okay, so we have multiplicity 2. Okay, and lambda 3 is -1. So we have 13 multiplicity for the root 2. Okay, now for this lambda 1, lambda 2, lambda 1 equal lambda 2 equal to 2, then A minus lambda will lambda I. Now, so this is A, okay, A minus lambda. So this will be, if lambda is 2, you see, if lambda is 2, so 2 minus 2 will be 0. Then we have a lot of zeros in this matrix, okay, this matrix. So the matrix A minus lambda I will be evaluated at lambda to be 2. So you can get, this matrix will be, let me write here maybe. This matrix will be, you have a lot of zeros, 0, 0, 0, 0, 0, 0. Okay, here you have -3, here you have 3, here you have 1. Okay, so we want to find the null space of this. Okay, find a null space of this. Now the null space, is the same if we do rule operations. Okay, we do rule operations. So if we do rule operations, so R1, R2, R3. So do rule operations, add -3 rule 1 to R2, replace R2, 3 multiple of rule 1 add to rule 3, replaced by rule 3. Then we get actually this matrix 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay, so you see here we only have one non-zero rule vector. So the rank of the rule vector is the rank of the rule space. Rank of A minus lambda I is actually 1. So null space, dimension of the null space will be 2. Now actually you can find this matrix 0, 0, 1, 0, 0, 0, 0, 0, 0 times XYZ. This will be X 0, 0. Okay. Sorry, it will be here. Sorry, it will be this will be first rule times, so this will be 0, this will be 0, this will be Z. Okay, so you see the null space is exactly when Z vanishes. Okay, we want to, if this is in the null space, this is in the null space A minus lambda I, if only if Z equal to 0, So actually the null space, so we have XYZ. Okay, we want this to be 0. Okay, so this tells us XYZ is in the null space of this matrix. Tells us this is equivalent to Z equal to 0. So i.e. null space is XY 0. Okay, XY plane. Okay, XY plane. Okay, so in this case, eigenvector will be V. This will be a vector will be XY 0. So it's X plus X multiple of 1, 0, 1 plus Y multiple of 0, 1, 0. Okay, so the eigenspace for this eigenvalue is the XY plane. Okay, the eigenspace for eigenvalue 2 is the XY plane, 2-dimensional. The XY plane, 2-dimensional. Now you see the multiplicity is 2. Okay, multiplicity is 2. Okay, so here the multiplicity for this eigenvalue, for this characteristic polynomial, this is here we have 2 eigenvalue with eigenvalue 2. This here we see this eigenvalue 2 has multiplicity 2. Okay, multiplicity 2. This is called algebraic multiplicity. Okay, algebraic multiplicity. Now here the eigenspace is XY plane. This is called the geometric multiplicity. Okay, geometric multiplicity. Be careful. In general, the geometric multiplicity is less than or equal to the algebraic multiplicity. Okay, they may equal, but in general, it is possible that the geometric multiplicity can be strictly smaller than algebraic multiplicity. Okay, so the algebraic multiplicity, and we also have the geometric. Okay, geometric multiplicity. They may differ. Okay, they may differ. But geometric multiplicity is always less than algebraic multiplicity. Okay, so this is for the eigenvalue 2. Now the eigenvalue -1. Okay, if lambda is -1, so the eigenvalue -1, so we get a subtract lambda I. This will be a plus I. Okay, this will be, remember A is 2, 2, 1, 3, -1 here, 1. Then all others are 0. Okay, so A plus I will be, we add 1 to the main diagonal, to every entry on the main diagonal. 2, 2, 1. So we get 3, 3, 0. And here we have 3, here we have 1. Then all other entries just be 0. Okay, so we want this vector, so we want to solve this linear system. 3, 0, 1, 0, 3, 3. Or you do, so here the rank easily same. The rank is 2. The rank is 2. The rank is 2, x, y, z. What we get is, this is 3x plus z. This we get 3y plus 3z. This we get a 0. Okay, this we get a 0. So we want this thing to be in the null space. We want this thing to be 0. Set this thing to be 0. Set it to be 0, 0, 0. Okay. So then we compare component wise. So we get a 3x plus z is 0. And a 3y plus 3z is 0. Okay. So we got a okay, so we got a z equal to, so we got a y equal to, so the first equation tells us x is -1/3 of z. The second tells us y is a negative of z. Okay, then the vector will be x, y, z will be substitute x by -1/3 z, subtract y by negative z, subtract z just by z. So it's z multiple of -1/3, -1, 1. Or you just factor out, multiply by 3 to clear the denominator. So the eigenvector will be, so eigenvector will be z multiple of -1/3, -1, and 1. Okay, here z is in R, and z is of course non-zero scalar. Okay, so you find all possible eigenvalue and eigenvectors. Okay, for this 3x3 matrix. Okay, now we study properties. Of eigenvalue and eigenvectors. Okay, first of all, okay, theorem. This is the easiest theorem. If lambda is an eigenvalue for matrix A, lambda is an eigenvalue of a matrix A, then lambda to the power k is an eigenvalue of a to the power k. That's pretty easy. That's pretty easy to show. Prove. Now here we know lambda by definition is eigenvalue. So this means A times some vector V equal to lambda V for some non-zero vector V. Now we apply A squared V. This will be A times AV. Okay. AV is lambda V. So this is A times lambda V. Now lambda scalar multiplication, you can factor it out. So it's lambda times AV. Now AV is again use that V is eigenvector. So it's lambda times lambda V. So this we get lambda squared of V. So etc. Apply A to the above equation again and again. So finally we get AK. Apply to V. This we get lambda to the power K V. So this means by definition, here V is non-zero scalar, non-zero vector. So we get actually lambda to the power K is indeed is an eigenvalue of A to the power K. Then we're done for this. Okay. The next theorem tells us that different eigenvectors correspond to different eigenvalues. They are linearly independent. Theorem. Important theorem. Okay. So assume we have n distinct eigenvalues. Assume that lambda 1, lambda 2, lambda n. Sorry, let's use lambda m. My notation lambda m is these numbers are m distinct. Here the distinct property is important. Distinct eigenvalues. Eigenvalues of a square matrix. Square matrix. We are talking about a square matrix for eigenvectors and eigenvalues. With corresponding in x1, xm are the corresponding eigenvectors. Corresponding eigenvectors. The conclusion is the m vectors correspond to distinct eigenvalues are linearly independent. Linearly independent. Okay. So distinct eigenvectors for eigenvalues, they will try to span as large space as possible. Okay. Okay. Proof. Now we need to show if we have a linearly dependent relation, i.e. the sum, scalar sum of the linear sum of these vectors to get 0 vectors, then this is only possible if we have the trivial linear combination. So assume we have some linear relation a1 x1 plus a2 x2 plus etc. plus am xm, so that we get a 0 scalar, 0 vector. Then we apply the matrix A. Here, I is in real number. I equal to 1 all the way to m. Then we apply the matrix A. Apply matrix A to the above equation. Okay, we let matrix A multiply a vector. Then use linear relation, we can distribute, okay? This multiplication is linear, so we can distribute to every term. So we get A1 x1 plus A2 x2 plus AM xm. Now a matrix times zero vector, of course we get a zero vector. So this we get, if you factor out the E1, so you get E1 E times x1 plus E2, linear property, A x2 plus EM AXM. This is zero vector. Now we use definition of eigenvector. Okay, so when we apply the matrix to the eigenvector, then we get eigenvalue times the eigenvector. So it's A1 lambda 1 x1 plus A2 lambda 2 x2 plus etc plus EM lambda m xm equal to zero vector. Okay, now of course we can apply matrix A again. So and then we multiply the eigenvectors again, eigenvalues again. So apply A again. So we get A1 lambda 1 squared. We apply A again. So we factor out a copy of eigenvector. Okay, lambda 2 squared x2 plus etc plus EM lambda m squared xm should be 0. Okay, now etc. So we can get many equations. We can get lambda yi x1 a1 plus a2 lambda y lambda 2 to the power I x2 etc plus em lambda m to the power I xm is 0. So now we write this thing as the matrix form. We write this thing as matrix form. Now be careful. We write in this form. Okay. So A x1, A x2. Root column vectors A m xm multiplied by this coefficients matrix is y y y. Okay, this is lambda y squared lambda y m. This we get lambda m lambda m to the power m. Okay, this is 0. Check this. Okay, check this. Check this. Okay, so the above equations can exactly written in this manner. Okay, in this manner. So if you write this as matrix B and this as matrix A, and this equal to 0. Okay, here A, so you write it as B times A is 0. Here A is invertible. YA is invertible because A is the one dimensional matrix. One dimensional matrix. Now it's invertible if not two pairs are same. Okay, so the lambdas, lambda 1, lambda 2, lambda m, they are pairwise distinct. Then we know the determinant is actually non-zero. Okay, actually we know how the determinant is. The Weinerman matrix. Okay, so we know determinant. Last time we did one example, Lewis 3x3 case of Weinerman matrix. We find its determinant. Okay, so determinant A squared is actually this lambda I minus lambda G squared. Yeah, so here so we let it, for instance, we can, so here remember, it's really annoying to remember the factors, okay, to remember the negative ones. So here we assume I less than J is less than from 1 to n, okay, from n. Here it's m by m, so it's a m. M. Okay. Okay, so here lambda I, lambda j, they are pairwise distinct. So the determinant is non-zero. Okay, it's non-zero. It's non-zero. So the determinant is non-zero means this matrix is invertible. Okay, this means A is invertible. Okay, this implies A is invertible. Invertible. Okay, it's invertible. So B times invertible matrix is 0. Now if you multiply by A inverse, this is 0 times A inverse, which is 0. Now A times A inverse is identity. Okay, B times identity is 0. So this tells us B. B times identity is B. This tells us B is the 0 matrix. Okay, B is the 0 matrix. Now the eigenvectors are non-zero. Okay, remember B is this matrix A1 x1, A2 x2. Okay, in column vectors am xm. Now each eigenvector is non-zero. Eigenvector by definition is non-zero. So this actually this 0 matrix, this tells us this is only possible if A1 is 0, A2 is 0. Em equal to 0. i.e., if we assume their sum is 0, then this is possible if the coefficient should be 0. Okay, so this tells us that x1, x2, xm, they are linearly independent. There's no relation between them, linear relation between them, are linearly independent. Linearly independent. Okay, we're done. Okay, we're done. So eigenvalues corresponding, eigenvectors corresponding to different eigenvalues are linearly independent. This is a really, really important property that we should know. Okay, that you should remember this conclusion. Okay, next property. Okay. Now remember when we solve the eigenvalue, we actually find zeros of the characteristic polynomial. Okay, so definition, we already defined it. Okay, so given a matrix A, so if you then A, so this, if you write a matrix A equal to this, matrix A equal to A11, A12, A1n. Okay, so it's n by n matrix. An1, Ann. Okay, so it's n by n matrix. Then A minus lambda I, this we get the diagonal terms A11 minus lambda, A22 minus lambda, Ann minus lambda. Okay, then all other entries just keep it fixed. A1n, An1, Only the diagonal terms we subtracted by lambda. So now if we take determinant, then the determinant A minus lambda I is a polynomial. Okay, is a polynomial in lambda. Okay, is a polynomial. Is a polynomial. If you explain it, is a polynomial in lambda. Okay, in lambda. This polynomial is called, which is called, we already see several examples, which is called the characteristic polynomial. Characteristic polynomial of the matrix A. Okay. Okay, so if we write f lambda, okay, as this polynomial, okay, determinant of A minus lambda I. So it's degree, so this, is of degree n. Degree is of degree n. Degree n. If you expand it by using the definition of a determinant, by the cofactor definition, you will find this is actually degree n. F lambda is always degree n. Okay, degree n. Okay, degree n. Now we study about this characteristic polynomial. Okay. Okay. Now, if we to determine a polynomial, it suffices to determine all its coefficients. Okay, all its coefficients. It's a finite degree, so we just determine all its coefficients. Now, if we write f lambda, right? So f lambda can be write as this form. So f lambda can be write it in this form. So the highest degree is lambda to the power n. Lambda to the power n. So it's negative. So the diagonal product of the diagonal terms, they gives you we have a bunch of a negative lambda. So they multiply, so they are n negative lambda. So the highest degree is given by -1 to the power n. Okay. So this bn minus 1, lambda n minus 1, plus etc., plus b0. Now the coefficients are very, very important. Okay, the coefficients are very important. Okay. Now what is f0? What is f0? What are f0? Okay, if we plug in f0, you see, plugging lambda by 0, f0 we will get a minus 0 times I. 0 times I just 0. So this is determinant of a. Okay, so f0 is determinant of a. Okay, now if we write in this term, so if we know, suppose, remember, the 0 of f lambda is the eigenvalues of a. Okay, suppose lambda 1, lambda blah blah, lambda n are the eigenvalues, not necessarily distinct. Okay, it's possible that the sum of lambda 1 may be equal to lambda 2, etc. So we may have multiplicity, so it's okay. So suppose we have the n eigenvalues are the eigenvalues of a, then we can write f lambda in this form. The lambda eigenvalues are the roots of the characteristic polynomial. So we can write so if you know the roots of a polynomial, all the roots of the polynomial, and know the highest coefficients, then you can factor a polynomial as a product over its roots. Okay, so then you can get actually this you get lambda I minus lambda. Okay, product I from 1 to n. You can check if you plug in lambda I, lambda 1, lambda 2, lambda n, you get actually exactly 0. And the highest coefficient is actually -1 to the power n. Okay, so this indeed this thing. So this equal to -1 to the power n lambda n plus b n minus 1 lambda n minus 1 plus etc. plus b0. Okay, now we take lambda equal to 0. The right side take lambda to be 0. Lambda to be 0. Take lambda to be 0. Then you have actually lambda f0 will be product lambda I minus 0. I from 1 to n. So this will be lambda 1 times lambda 2 times lambda n. So we get this property. So the product of all n eigenvalues is the determinant. So remember, f0 is determinant of a. Okay, so we get this property. Product of eigenvalues is the determinant of this matrix A. Okay, so get this. Determinant of this matrix A is the product of its eigenvalues. Okay, I from 1 to n. Okay, determinant of a matrix equal to product of all its eigenvalues. Okay, product of eigenvalues gives us determinant of this matrix. Okay. Okay. Now, so the highest coefficient is -1 to the power n. That's not interesting. Then the next leading coefficient, degree n minus 1. So the next coefficient, here, let me label that thing in red. Okay, so the term Bn minus 1, the term Bn minus 1. Now you can use the definition of determinant when you expand the determinant. So you can actually get the next leading coefficient, Bn minus 1. Okay, so what is the next leading coefficient? Okay, so if you have, remember, f lambda, so we have f lambda to be lambda I minus lambda. So if you find the coefficients of degree n minus 1. So the degree coefficients of the term. So this algebraic problem, coefficient of lambda to the power n minus 1. This is given by, okay, so this is the combinatorics problem. You choose n minus 1 factors of negative lambda, and then the other you choose lambda I from the one of the n choice. Okay, so this you finally get -1 to the power n minus 1 times lambda I. Okay, sum of this lambda I from 1 to n. You have n choice. Each choice gives a contribution lambda I times -1 to this power n minus 1. So all this contribution is sum them together gives us the coefficient of lambda to the power n minus 1. Okay. Okay. Now how do we fact this sum of this lambda I equal to the sum of the diagonal entries. I from 1 to n. Okay. It's not difficult to show this. Okay. Just algebra. Use a little bit of algebra to show that that the sum of the roots is actually the diagonal terms. Okay. Okay, so here this quantity, sum of this thing, sum of the diagonal entries, they are called the cheese of the matrix. Okay, they are called the cheese of the matrix. So definition. Cheese A is defined as AII, so it's n by n determinant, n by n matrix. Okay, sum of the main diagonal entries. Okay, and this equal to lambda I. Okay, sum of its n lambda values. So this cheese is super important in linear algebra. Okay, super important. Cheese. Okay. Okay, let's see this example. Example. Maybe we give an example. Okay, we have a lot of examples. Remember, okay, just see one example that we already did. So A is, for instance, is 3, 3, -1, -1. So cheese A, you see, cheese A is sum of the diagonal terms. Okay, 3 by So A11 plus A22. So A11 is 3, A22 is 3, so it's 3 by 3, sum, we get a 6. Okay, now, remember its characteristic polynomial, determinant of this matrix, 3 minus lambda, 3 minus lambda, -1, -1. So this we get 3 minus lambda squared minus 1, -1 times -1. So you get 3 minus lambda squared minus 1. Okay, this you get, if you expand this, okay, then you get, then what you get is, or you use this thing, 2 minus, use this square, some difference of 2 perfect squares. Okay, so you got a 2 minus lambda times 4 minus lambda. So we have 2 eigenvalues. Okay, so eigenvalues lambda 1 equal to 2, lambda 2 equal to 4. Okay, you check lambda 1 plus lambda 2 is 2 plus 4, which is 6. Okay, so you see this is exactly 6. Okay, so 6 equal to 6. Okay, so we compute it by 2 ways. Okay, you get a 6 equal to 6. The sum of the eigenvalues equal to the sum of the diagonals, main diagonals, sum of the main diagonal entries. So trees is a really important quantity. Okay. Property of okay, this property of trees. Property of trees. Okay. Now remember we have f lambda to be determinant of a minus lambda I. Okay, so here lambda is a scalar. Lambda is a scalar, so this is a polynomial. Okay, polynomial. However, if you replace lambda by a, if you formally subtract lambda by a, if you formally substitute the lambda by a, so lambda times I will be a times I will be a minus a will be 0. So the next thing is says next theorem, Cayley-hamilton theorem says this f lambda, if you replace lambda by a, okay, you get a 0 matrix. Okay, the 0 means 0 matrix, okay, matrix, 0 matrix, i.e. if you plug in a to the characteristic polynomial, you get a 0 matrix. Okay, so here the proof, we will not talk about the proof. Okay, the proof is beyond the scope of this course. The proof is out of the scope of this course. If you go to graduate level course, then abstract algebra, then or community algebra, then you will see a proof there. Okay. Now, of course, you can check. We will not prove, but you can actually check the examples. We will not check. You can check this yourself with the examples that we had. Okay. So property of trees. Properties of trees of a matrix. Trees operation. Okay, first of all, property 1. Trees of AB is equal to trees BA. Okay. I.e., if you have 2 matrix product, okay, then you actually have trees AB equal to trees BA. Now be careful, be careful. Before we prove, you should be careful. Now, if you have 3, now you cannot rearrange the order as you want. So it's not totally, forget about order. So you can get a choice. You can write A times BC. So you can view BC as one matrix. So use this equal view A as matrix. So you get a BCA, choose BCA. Okay. Now this also equal to choose if you write it as BCA as you see BCA. You can also flip. You get a CAB, CAB. Okay, CAB. If you switch again, okay, switch again, then you actually get choose ABC. Choose ABC. Okay, so so if you write ABC as this manner, ABC as let's see this, you see AB times C. Now you have choose ABC equal to choose CAB. Okay, you see, you never have this BAC. Okay, you never get a BAC. It's possible that they have the same choice, but in general, it can fail. Okay, so you have something missing. So for 3, you don't get arbitrary order. Okay, you don't get arbitrary order. Some order is not there. Okay, be careful. Doesn't mean it's totally commutative when you take choice. Okay. So this is really tricky. This is really tricky. Now we prove. So this is not is missing. So you don't get this thing in general. So let's see how this works. Okay. So if we write C to be the product A times B. Okay. Let D to be BA. So we want to choose C equal to choose D. Now choose this AB is a choice of C. So this sum of the diagonal terms CII, I from 1 to n. Now CII equal to, now the product, C equal to AB. So it's AIJ. So it's AIJ. So CII. So CII equal to AIJ times BGI. Sum over I. Sorry. So this is sum over G. So this is CII. And then we sum over I from 1 to n. Okay. Okay. Then choose BA. Choose BA. This will be choice of D. Now this will be sum of D I from 1 to n. Now this will be sum of DII I from 1 to n. DII will be sum over J. Okay. D is B times A. So it's B J I. Sorry. Sum over G. Sum over G. So it's IJ BIJ times AGI. Okay. G is from 1 to n. Okay, now if you switch, now remember, addition they are commutative, so you can switch this summation. Final thing, you can always do that. Okay, so you get a AGI, BIJ. Okay. Did I miss something? So here, just manipulate. So let me change the index. So here, let's use the letter J. So we just rename the variable. So this is easier if we rename the variable. So here, this sorry, J is from 1. Let's it to be DJJ is okay. It's BJI Aij. Okay, so it's I from 1 to n. Okay, now we switch the summation. We switch the summation. So I from 1, G from 1. Okay, switch the sigma notation. Okay, so this will be Bij, Aij, Bji. Okay, this is exactly, you see, this is the exact choice of AB. Okay, just double check. Okay, so you see this looks exactly the same. This is exactly the same. After we rename the variable. Okay, rename the variable. They are the same, exactly the same. So we get, we are done. Okay, so we get choice AB equal to choice BA. Okay, so we are done. So we get done. So choice AB equal to choice BA. Okay. So although matrix multiplication in general is not commutative, matrix multiplication is not commutative. However, we recover the commutative property once we take the choice. Okay, take the choice. So this is actually nice property. Nice property. So because the commutative law is nice property. Okay. Once we take the choice, we recover the commutative property for two matrix multiplication. Now, in general, you should be careful. For three matrix, we don't get arbitrary order. We don't get arbitrary order. The order actually matters. Okay, so it's not completely commutative when we take a choice. Okay, the second property is the following. Second property. If P is invertible, then we have the same choice. These two matrix, choice P A P inverse and choice A are the same. Okay. Definition. Let's give a definition. Two matrices A and B are called similar. If B equal to P times A P inverse for some invertible matrix P. Okay, they're called similar. So this tells us similar matrices have the same choice. Now we will prove a stronger property. We will show that, you know, the choice is determined by the characteristic polynomial. Okay. Now eigenvalue is also determined by characteristic polynomial. So we prove stronger property, i.e., similar matrices have the same characteristic polynomial. Okay. We prove this theorem. Similar matrices. Okay, similar matrices have same characteristic polynomial. Have the same polynomial. Characteristic polynomial. Same characteristic polynomial. Okay, prove. Right, A and B, they are similar. So suppose B equal to P A P inverse is similar matrix, is similar with A, Then the characteristic polynomial, you see, then the characteristic polynomial of B. So the characteristic polynomial, polynomial of B is this, okay? Determinant of this B minus lambda I. Now this is determinant. B is P inverse minus lambda I, okay? I, we can write lambda I we can write as lambda P inverse, because P inverse, okay, I times P inverse is P inverse, and P times P inverse is I, identity, okay? So we can write the thing as determinant P inverse minus lambda P inverse, okay? Now you can write it in this form. So this is the determinant of factor out P A minus lambda I times P inverse, okay? P inverse. And the determinant of a product is product of determinants, okay? For the matrix operation. So it's determinant of P times determinant of A minus lambda I times determinant of P inverse, okay? Now the determinant, you can remember determinant, they are numbers, so we can switch them. So it's determinant A minus lambda I times determinant of P times determinant of P inverse. Now determinant of a matrix P and determinant of P inverse, they are, reciprocal, okay? Or you use the property of a determinant. So this determinant of A minus lambda I times determinant P times P inverse. Determinant P times P inverse is determinant I. Determinant of I is 1, okay? So this is determinant A minus lambda I times determinant of identity matrix, which is 1. Determinant A minus lambda I times 1, okay? Determinant I is 1 times 1 just itself. So this is actually equal to, by definition, characteristic polynomial of A. Characteristic polynomial of A. Then we're done. So characteristic polynomial of B equal to characteristic polynomial of A, okay? So we're done, okay? So similar matrices have the same characteristic polynomial, okay? As a special case, okay? The choice is determined by the characteristic polynomial. So here choice, so we get a choice A equal to choice P inverse. And we can also, of course, prove it by the property of a choice, by the property 1, commutative property, okay? So we can also prove 1. We can also prove this property by property 1. We can also easily prove this. We can also prove this property by 1. By property 1. So for instance, choice P inverse. You write it as choice this matrix P times A P inverse. Okay, this matrix. Okay, and then switch. This is the choice of A P inverse times P. Okay, switch. Use property 1.
我刚要电话，我去给那康碧打电话，康碧说那个。
Okay, so this will get choose A P inverse times P associated property. So this is A times P inverse times P. So this is choose A P is invertible. So P inverse times P is identity matrix. Now identity matrix is multiply any matrix A, we get just matrix A. The choice of A. Okay, then we're done. Okay. Now we estimate how big. Now Eigenvalue and eigenvectors are important for a matrix. Now, remember to solve eigenvalue, we need to solve equations. Okay, find the root of polynomial, the characteristic polynomial. For last degree, it can be computation. The computation can be expensive. Okay, computationally expensive. So which means we can, if we can estimate it, it will be good. Okay, by directly compute the eigenvectors, eigenvalue and eigenvectors. Okay, so now we give a bound, control the eigenvalue by the interest. Okay, so estimate of the eigenvalues of a matrix A. Okay, so this is the next section. Estimate the eigenvalues of a matrix A. Okay, theorem. Every eigenvalue lambda of a matrix A is, we can bound it by third circle. Every matrix eigenvalue lambda of a matrix A, I mean a square matrix. So we just by default assume A is square matrix, is in the circle, around one of the main diagonal entries. One of the main diagonal entries. Okay. So here is this this circle AII minus lambda. So lambda is a variable. Be careful. This lambda can be a complex number. Okay, complex number. So this norm is complex norm. This is bounded. So if it's a real, it's just a real norm. Okay, real norm. Okay, so here the radius I are the radius Ri is defined as the sum of this of diagonal terms. G not equal to I. Okay, here I is fixed. G is ranging from 1 to n, and G is not equal to I. So G is less than equal to n, greater equal than 1. So it's n by n matrix. Okay, now we actually use the property that we proved one time, that the diagonal dominant matrices are invertible. Okay, diagonal dominant matrices are invertible. So prove. Now we prove. Now if AV equal to lambda V, okay, suppose AV equal to lambda V. This definition for eigenvalue and eigenvector. So for some non-zero vector V, then we have, if you write in this form, A minus lambda I times V just V. I is identity matrix. This equal to 0. You can easily write in this form. So this tells us that the matrix, the V is in the null space of the matrix A minus lambda I. Okay, so this means A minus lambda I is singular, not invertible. Okay, i.e. not invertible. Remember, diagonal dominated matrices are invertible. So here, this matrix A minus lambda I is not invertible, okay? Which means this A minus lambda I is not diagonally dominant. It's not diagonal dominant. Diagonally dominant. So, not diagonal dominant. So this means its diagonal is dominated, okay? The diagonal is dominated by the off diagonal terms. So it's not diagonally dominant, means the diagonal is dominated by non-diagonal entries. So which means the diagonal, you know, so at least for some of the things, so at least one of the diagonal should be dominated by the off diagonal thing. So the diagonal for some I is diagonal entry is at least for some I is dominated by the off diagonal entries. Okay, some of this of the value of the off diagonal entries. So here G not equal to I means this is off diagonal entries. And this is the radius of I. Radius R. So this means this thing should be true for at least one I. Okay, because if this is the greater equal than, then this means the matrix A minus lambda A is dominated, diagonal dominated. So this should true hold for at least one I in 1, 2, 3, 4 all the n. Okay, at least one of the things should true. Okay, so this means lambda is liking one of the circle. So this equation is the circle. Okay, if you write lambda as a complex number, so this is actually a circle. Okay, so this defines the circle around AII. Okay, some example. Example A is, for instance, ABCD. Okay. Okay, then here we have lambda minus A, then lambda should satisfy A minus A less than or equal to B, or so the two diagonal thing, okay, would be lambda minus D. Now off that is the second thing, the second I equal to 2, so it's I equal to 1. I equal to 2, lambda minus A to 2 less than or equal to C. Okay, so there are two circles. So lambda should satisfy one of this equation. It's possible that lambda satisfy both, but lambda should satisfy at least one of this relation. Okay, so these two circles, they are called this name, Gauss-Green circles. Okay, so we have a control about how big the eigenvalue should be. So we have a control of the eigenvalue by the inches. Okay, homework for this section. Let's see, this section is 6.1. Okay, this 6.1. 6.1. Number 4, number 13, number 17, number 18. Okay, we have 20 minutes. Now let's start with the next section, the diagonalizing a matrix. Any questions so far? Okay. Okay, let's start the next section, diagonalizing a matrix. Diagonalizing a matrix. Okay. So some diagonal matrix, they are easy. Okay. So suppose we have a diagonal matrix. Diagonal matrices are easy because they are commutative. They are easy to do with. Suppose gamma, the matrix gamma is lambda 1, diagonal matrix with diagonal entries lambda 1 all the way to lambda n. Okay. So to give a diagonal matrix, it is suffice to give all the numbers, any numbers along the main diagonal. Okay. So we just write it as lambda 1, lambda n. Okay. So let this gamma be a diagonal matrix. Diagonal matrix. Now, if you write in this form, so gamma is n by n matrix. Gamma is, you see, it's a lambda 1, lambda 2, lambda n. Then all other entries are 0. Okay, so now remember, once we have a matrix, then this matrix gives us a rule that you input a vector, output a vector, okay, by multiplication. So then you can check if we let E1 to be this vector 1, 0, bounds of 0. Now E2 is the second entry is 1, then all others are 0. En is the 0, 0, 0, then the last entry is 1. Okay. Then you can check. Okay, the output of E1 if we use this rule. So the gamma tells us if you input E1, the gamma will output the first column. Okay, the first column is, you see, this will be lambda 1, 0, bounds of 0. So this is the lambda 1 E1. So similarly, if you plug in E2, so gamma E2 will output the second column of gamma. So it's 0, lambda 2, 0, bounds of 0. So if you factor lambda 2, so it's lambda 2, 0, 1, 0, bounds of 0. So it's lambda 2, E2. Okay, so what this matrix gamma does is we plug in E1, we get lambda E1. Plug in E2, we output lambda E2. So just rescue the orthogonal basis, okay, E1, E2, En, okay, etc., etc. So this diagonal, what is a diagonal matrix does is it just rescue the orthogonal basis, lambda 1, lambda 2, lambda n. So it's lambda n, En, okay. 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 So this is what a diagonal matrix does, okay. Now, suppose we have matrix A with, you see here, we have eigenvectors. So IE, by the definition of eigenvectors. So E1, En are eigenvectors. Eigenvectors of the matrix gamma corresponding to eigenvalues. Corresponding to eigenvalues lambda 1, lambda 2, lambda n. Okay. Now, if we have a matrix A, now given a matrix A, matrix A with eigenvalues, with eigenvectors. Suppose this matrix has n linearly independent eigenvectors with n linearly independent eigenvectors. Let's see, v1 dot 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 vn corresponding to eigenvalues corresponding to eigenvalues, lambda eigenvalues, lambda 1 dot 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 lambda n. Okay, then we have, by definition, A v1 is lambda 1 v1. Okay, so A v2 lambda 2 v2 dot 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 A vn equal to lambda n vn. Now you see A v1. So what this matrix A does is A rescue the eigenvectors v1, v2, vn by a scalar. Okay, you see here the matrix. You see if you write together here. Remember, so this is for A. Remember, we have what this diagonal matrix does. A E1 is lambda 1 E1. Gamma E2 is lambda 2 E2. Dot dot dot. Gamma En is lambda n En. So you see, this looks like similar thing. Okay, if you replace E1 by V1, okay, this will be the same thing. Okay, if you replace, if E1 is V1, okay. So what this matrix A does is the matrix A rescue the eigenvectors. Okay, now the diagonal matrix gamma rescue the orthogonal basis vectors E1, E2, En. Okay, rescue it by the eigenvector lambda 1, lambda 2, lambda n. Okay, now A also rescue eigenvectors lambda 1, lambda 2, lambda n by this scalar. Okay, so the conclusion is the action of A on its eigenvectors looks like that of a diagonal matrix. So the action, what this matrix A does on its eigenvectors, the action of A on its eigenvectors, on its eigenvectors looks like or similar, looks like that of a diagonal matrix, that of a diagonal matrix on the basis vectors E1, E2, dot 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 En. Okay, now we do a base change. We change E1 to V1, E2 to V2, so that actually this will be exactly tells us the relation. Okay, tells us the similarity between these two things. Okay, so we change bases. Okay, so we do base change. Okay, remember this n vectors. Now v1 dot 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 vn, by our assumption they are linearly independent. So they form a base. Are linearly independent. linear independent. So they form a base. So they form a base. Form a basis. So we do base change. So we do base change. We do base change. Base change. So we want to do the base change. We want a matrix X that we plug in E1, we get a V1. We plug in E2, output by this rule, we get a V2. Okay. Plug in En, we get this Vn. Okay. Now remember, a matrix n by n matrix tells us now the image E1, E2, En is actually column vectors. Okay, column vectors. So in matrix form, so this actually tells us what this column vector X is in matrix form. In matrix form, or in matrix representation. Representation, this means we use the matrix to write down how this matrix does on vectors. Okay, so this what is the word representation mean? Okay, representation tells us we write it as a matrix. Given an action, we write it down is formed as matrix V1 Vn. Okay, so what we do is we write this V as column vectors. Okay, V1, V2, Vn. Then you can check V1, this X multiply E1. Then you can check X times E1, you get a V1. X times E2, we get a V2. So we just change E1 to V1, change E2 to V2. Okay, so this is what this matrix does. Okay. Now remember Vn, they are actually V1, V2, Vn, they are linearly independent. So this means X is invertible. Okay, X is invertible. Now remember, change base. Two bases, they can change back and forth between them. Okay, so X is invertible. X is invertible. So X is invertible. So we can find X inverse. Okay, so you see, if we start with E1, then we do X, then we get a V1. Okay, then we get a V1. V1, remember, V1 is exactly the eigenvector of A. Okay, so this you gotta apply A, we get a lambda 1. Okay, when we apply A to this eigenvector, we multiply by a scalar. Now we do the inverse. Okay, so this is X. Now X inverse, what X inverse does is, so X does is we plug in E1, we get a V1. Now X inverse, we plug in V1, we use X inverse, the inverse operation, then we get E1. Okay, now V2, we get a X inverse, we get a E2, etc. blah blah blah. Vn, X inverse, then we get a En. Okay, now we apply X inverse. Okay, X inverse, then we get, remember, X inverse map V1 to E1. So it's lambda 1 E1. Okay, scalars are fixed. Okay, so you see, now E2 under this rule, X, we get a V2. Under A, we get lambda 2 V2. Now apply X inverse, change base back. Okay, then we get lambda 2 E2. Okay, etc. etc. You see, En under X, you change it to Vn. Now apply A, you multiply by lambda. Apply X inverse, so we get lambda n En. Okay, so if you view this as a black box, so this matrix multiplication by X, then multiplication by A, then multiplication by X inverse. So this matrix, this operation, so the matrix satisfies X inverse AX satisfies we plug in EI, output lambda I EI. Plug in EI, output lambda I EI. This is exactly what the diagonal matrix does, okay? This is what a diagonal matrix does, okay? This is exactly what a diagonal matrix does, okay? Okay, a matrix, remember a matrix is a rule, tells you what do you get if you plug in a vector, okay? Now these two rules are the same, okay? This matrix X inverse AX and the diagonal matrix, they tells us the same rule, okay? Plug in something, output something, okay? They gives you the same rule. So this tells us that they are the same rule. They are actually the same matrix, okay? So this tells us this thing is actually gamma, the diagonal matrix. So X inverse AX is the diagonal matrix. So it's diagonal matrix, lambda 1, lambda n. Okay. So then we can solve for A. Okay, we can solve for A. So A you can get, so we get X inverse A, X is gamma, so we multiply X to the side. So X inverse AX is X gamma. Okay, so you see left multiplication by X. Okay, so multiplication by X on the left. Multiplication by A on the left. Then we get the thing. So use associative property, X times X inverse. They cancel out each other. So identity. So get AX equal X gamma. And then we multiply X inverse. Multiply X inverse on the right. So we get A times X inverse. This is X gamma X inverse. So X times X inverse is identity. So we get A is A equal to X gamma X inverse. Okay. So by definition, a matrix, so X is inverse, X is invertible. So, so you see what happened is a chain of bases. So matrix, we have similar matrix. So A is similar with a diagonal matrix. Okay, A is similar to a diagonal matrix. Okay. Now this is the general principle. If you change bases, so change of bases. So at the matrix level, you have, so at the matrix level, we have similar matrix. Okay, matrix level, similar matrices. Okay, now at the base level, this corresponds to change bases. Okay, now if you change a basis, then what the operation for matrix level is you use similar matrix. Okay, using, so a chain of bases corresponding to an invertible matrix X. Okay. Okay, so here we can write A as similar with diagonal matrix. Okay, now diagonal matrix, they are easier to deal with. Okay, if A is similar to a diagonal matrix, then it has, we can easily deal with it because it shares similar property with a diagonal matrix. Okay. Next time we will use this kind of similar property, okay, and study what nice property a matrix has. If it is, we can write it as a similar matrix of a diagonal matrix. Okay. Next time we will talk more about how we apply this nice property, okay, to get something interesting. Okay, let me stop here for today and continue tomorrow.